My friend VITOR M.M is professor of the University of Porto, Portugal, and is also research of IMPA. He usually works in Riemann problems in conservation law with stability, bifurcation, on geophysical model. Today speak about on porous media flow for 3 components on 2 phases. Please.
Thank you. This is new work. We are starting to study a class of problems, and here we present our first results on this model. We are concerned about the porous media filled with 2 phases, a gaseous and a lake, and with 3 components. One of the components, the insoluble gas, lives only in gaseous phases. That oil lives only in liquid phases, and there exists an oil that is volatile and can move from the oleic phases to the gaseous. We assume that the thermodynamic equilibrium is achieved every time. The temperature is constant, and the gradients of pressure are so small that you can assume constant pressure. So we have a lot of simplifications here. Like you assume that the gas and liquids are ideal, and some assumptions on viscosity and in the equilibrium between the vapor and the oil in the oleic phase. So we have a lot of constants. The constants has capital letters, so here everything is a constant. And by the other hand, if we have small these letters that are not capital, this is the actual value of the constants. We work with 2 kinds of variables, the molar fractions and the molar densities. Sometimes it's easier to understand if you work with molar fractions, but in the conservation laws it's easier to work with molar densities. So we have these 2 ways to describe the problem, and usually we use the molar fraction. This is the molar fraction of the oleic phase, the dead oil in the oleic phase. We assume the gas viscosity is constant, and the viscosity, well, this is B and D. And the viscosity of the 2 oils in the oleic phase are not equal in that way. The Reynolds law has how the equilibrium between the volatile oil in the oleic phases and in the gas occurs in this way. The ideal liquid in the oleic phase is a liquid if we join 2 volumes of 2 components. When they are joined, the total volume is exactly the sum of the initial volumes. So this gives us density of the oil phase, and we can write directly these equations. We assume a non-natural or non-physical variation of the viscosity of the oil, depending on the molar fraction of the dead oil. Usually, this relation is more hard to handle, so we choose this linear behavior because it's easier. But we believe that the solutions are quite similar if you use here something more sophisticated. As usually, we have the saturation of the oil, saturation of the gas phases, the fractional flows, the Berkeley-Leverett equation. Here, This is the ratio of the viscosity of the oil and the viscosity of the gas. This is a constant, and this depends on the molar fraction of the dead oil. To write the conservation laws, it's better to use the molar densities, and we have here a source term that is related with the evaporation of the volatile oil. I wish to remember you that the temperature is constant, so this evaporation doesn't occur by the temperature, but by other hand, because the displacement of the gas makes that the equilibrium is not reached, so some of the oil needs to go to the gas or vice versa to keep the equilibrium. Handling these equations in the usual way, we find a conservation law system, and this system has a property that we like to study. The accumulation depends only in two variables, the saturation and the molar fraction, but the flux depends on three, a velocity and the same two of here. So when we look for the eigenvalues, we have generalized eigenvalues because this matrix is singular. So the generalized eigenvalues are not equivalent to the usual eigenvalues. And for a 3 by 3 matrix, we find only two eigenvalues. One associated to the saturation and is the Buckley-Leverett velocity, and other associated to the evaporation, and is given by this equation, where this omega, capital omega, is given by this. We assume that this constant, that is the molar fraction from a pure component of volatile oil, is lower than the molar density of gas. This means that we may change the composition of oil, and you're still having always gas. We assume that molar density of the gas is lower than the dead oil, and the molar density of dead oil is lower than the volatile oil. Here, it's important to note that if we are talking about mass densities, usually a dead oil has a greater mass density than a volatile oil, but the reverse occurs if we are talking about the molar densities. So we assume this, and we can prove that omega is always negative, and this eigenvalue is well defined. Well, here I show an example for these values. These values, these constants are completely non-physical. So for sure, from here, this is a toy model. No chance to be something real. And why we choose these values? Because with this omega has huge values, 0.2, for instance. And with this kind of value, we can make pictures. Usually, physically, this is a very, very small value, negative. You can prove it, but so small that it's really hard to see the pictures. So now we are just trying to understand the solutions, and then someday we can put more reasonable values or physical values. Well, the two speeds one of them is the Buckley-Leverett speed. It's the derivative of the fractional flow function, and the other eigenvalue is the slope of this straight line that starts in minus omega to the point. So it's really simple to understand what is happening because it's quite visual. For instance, the coincidence, the point where the two eigenvalues are equal. Well, the interpretation is extremely easy. It's when this straight line is at the same time the line that passes here and there and is a tangent too. So we have two coincidence points for each value of y that we choose. Actually, the coincidence is a 10-degree polynomial in saturation and molar density, and we are able to prove that. For instance, here we have a curve because the gradient of this polynomial is vertical. So we can prove a lot of things, but here I will show only the pictures because it's easier to understand. So we have the evaporation eigenvalue as the faster eigenvalue in this zone and in this zone here. And in the middle is the Buckley-Leverett velocities greater than the evaporation velocity. If we look for rarefactions, it's really easy for the Buckley-Leverett velocity because the eigenvector is always horizontal. So the rarefactions are horizontal lines. For the evaporation, the eigenvector is not horizontal except in the coincidence, because here we have only one eigenvalue and one eigenvector. So this allows us to understand that actually this point is not only the coincidence, but is also the inflection of the eigenvalue associated to the evaporation, because here y is fixed, and we only can see what happens if s changes. And obviously this is a minimum for this eigenvalue. But because exactly here the eigenvector is horizontal, we know that here we have inflection point too. So this curve is the coincidence, and at the same time is the inflection of these rarefactions. Here I use the blue for slow waves, red for fast waves, and in this picture I distinguish the rarefactions associated to the Buckley-Leverett velocity with two lines and just one line for the evaporation rarefactions. Since this is a minimum, this rarefactions increase the velocity to the right, and here the velocities increase to the left. The Buckley-Leverett velocity increase always to the right because I'm just taking into account this part of the domain. Here it will be exactly the opposite. So now I'm concerned about this region. We are able to prove that the Hugonnet curve has a horizontal branch. It's really common, this occurs, and the velocity is given by this equation. So we have also, you prove also that if a certain quadratic condition on the left state is satisfied, and usually this is a universal condition, so every U minus satisfies this condition. For each W minus, there exists right state on the Hugonnet curve, horizontal part of the Hugonnet curve, where the velocity of the shock is equal to both sides is equal to the evaporation eigenvalue. Well, after proving this, we realize that it's easy, extremely easy to understand this in the graphic, because the point, we are here, and the velocity associated to the evaporation is the straight line that goes from here to there. Well, if is cross this in another point. This is the velocity of the shock that is equal to the speed in this side, and obviously is equal to this speed here. So we have the three speeds equal trivially. So for each point here, we have another here where the speed of the shock is equals the characteristic speed in the both sides associated with the evaporation wave. I'll show you a solution for a simple case close to the coincidence. The Huygens curve has a horizontal branch. This is a two-shock in the lax sense. And after that point where we have the double characteristic shock, this is a one shock. Because here the problem is hyperbolic, as usual, we have a shock branch here, two shock and one shock, and also one rarefaction and two rarefaction. Well, what happens now? After one wave, we can put two rarefactions. So after this one rarefaction, we put two rarefactions, and here we do the same. But it's also true that after one wave, we can use a two-shock wave. So we have two shocks to there and two shocks to there. And here, this is the point where the shock is characteristic in both sides. So here we have a one shock from there. And one shock is not available to put after one rarefaction. So here our solution must stop. But it's easier to see that if the speed is characteristic, we can go out with a two wave. So we have this kind of diagram for the solution near the coincidence. I will show you an example. I remember that this is a toy model, so the solution will look like a toy model too. I will show you how to solve this problem with this diagram. Well, for instance, suppose that here we have a saturation of 17.5% of oil, and in the right state we have the same saturation. So the only difference between these 2 points is the composition. In the right state we have half of depth oil, half of the volatile oil, and assuming, just like in the toy model, that this relation is 1/2, so the molar fraction of the volatile oil in this part should be 1/2 of the molar fraction molar of the volatile oil here. So we have half of 15%. And this side, we have 80% of the fraction molar of volatile oil. So we must have 40 there. So this is the Riemann problem, and the solution is one shock with only the saturation that change and the composition remains the same, an evaporation wave where the composition and the saturation change together and is a shock too, and then a rarefaction wave where the composition remains the same. And the picture is something like this. A shock where the saturation changed, but the molar fraction remained the same. So the composition is the same, both in the gas phases and in the lake phases. Then we have this shock here that is represented here, where both saturation change and the composition too. From here to here, the saturation changes from these values to that values there. And then we have a rarefaction where only the saturation changes, and the molar fractions remain the same. Okay, this is a solution for these 2 points, and the other follows the same idea. Future work. At first, we need to solve the problem for all right and left states. In the case that the saturation of oil is 0 or 1, we have single phases. So we need to join the 2 solutions, the solution of 2 phases to solutions of 1 phases. Probably with some more simplifications, could be possible to use the GLIM method to prove some Cauchy problems. Is one thing that we can do with this system. Other thing that we can do is improve the physical model. Now is a toy model, just a toy model. Then we can put more reasonable constants. So there are a lot of work to do in this kind of problems. Thank you. That's all.
Questions, comments?
No energy equation. So the evaporation is only because the gas